Okay, so let's put this into practice. Okay. Let's look at the graph of this function right here. It continues on downwards. Here's the graph of f of x is equal to minus x squared plus 4. And we want to find the area of this shaded region right here. Okay. Well, where does our shaded region start? It starts where? At what x value? At x equals 0, and we compute it until we get to x equals what? What's that intercept? What's that intercept? 2. Okay. All right. So I might just show you a curve. Okay. So the first thing you do is know how to translate that curve question into a calculus question. Okay. So everyone, let's write the definite integral from x equals from x equals where? 0. We customarily go left to right on this. X equals 0 to x equals 2 of negative x squared plus 4 dx. Okay? So what does that represent? I know it looks similar to our antiderivative symbol, but what does it represent? It represents the net area underneath the curve. It is the definite integral. Okay? Hopefully you're no longer calling it the s thingy, but I need you to take it one step further. Okay? We need to call this the definite integral versus the indefinite integral. Okay. So, well, that's a lovely thing to write, but how do we actually compute it? Well, in section 5.2, we will compute a couple of these the long way, and we will find out just how miserable that is. It's kind of similar to when we did the limit definition of the derivative. There is a limit definition to the definite integral, and we will do a couple of those by hand, but not many, because they are tedious, way more tedious than finding the limit definition of the derivative. Okay? But we're skipping to the main result here, which is the fundamental theorem of calculus part 2, which says rather than worrying about the definition of this, we can go ahead and just give an antiderivative of this function evaluated at the 2 endpoints. Okay? Now, that task of expressing this thing right here, an antiderivative evaluated at the 2 endpoints, that's way too much generally for us to do in one step. So usually we do it in 2 steps. In the first step, we find an antiderivative, reminding ourselves to evaluate it at the 2 endpoints, and then in the second step, we do it. Okay? So what is an antiderivative of our integrand thing inside the integral? What's an antiderivative of that?
X to the third over 3 plus 4x plus c.
Close?
1/3 x to the third.
Well, yeah, he said over 3, but what's the sign on it?
Oh, negative.
Yeah, so we get negative 1/3 x cubed plus 4x. Now, I said I just need you to give any antiderivative. So here I'm not asking for the antiderivative, right? So I'm not going to put plus c here. Okay? In fact, I'm not going to write anything there. By not writing anything there, what am I choosing as the constant? I'm choosing 0. Okay, that's the best choice to make. All right? Now, careful. What type of object do I have on the left here? What type of object is this?
Definite integral.
The definite integral, which is a value, which is a number, right? What's over here? Does a number equal a function? No. So this is supposed to read evaluated at the 2 endpoints. So what I do is I just remind myself to evaluate it at those 2 endpoints. Okay? I don't have a name for that symbol. I just call it the evaluation bar. Okay? I don't know if there's a name for it. I can't remember. We just write it. Okay? Don't forget it. Otherwise, you've said that a number is equal to a function, which is not true. Okay? So how do we actually use this? What this is just a reminder step that's going to say now, take the upper limit of an integration, plug it into the function, plug it into an antiderivative, minus the lower limit of integration. Okay, how are we doing? So let's see here. Let's clean this up. Let's see. 2 to the third power is 8, so we get minus 8 thirds plus 8 minus a bunch of zeros. Okay. So we get, let's see here, 8 minus 8 thirds. That'd be 24 thirds minus 8 thirds. I think we get 16 thirds. Okay. What does that 16 thirds represent? That area of the green shaded region, right? So if you had this parabola in your living room and you wanted to carpet it, how much carpet would you buy? You'd buy 16 thirds square feet or whatever your units are of it. Okay? That's the real world interpretation of this. Okay. Let's do it again. Okay. Let me just take this question over to another spot. This is for number 5, but I just... All right. So for number 5 here, let's find the area of this shaded region. Okay, it's going to look similar. Okay. It's still going to be the function f of x is equal to... It still goes down this way. It's still going to be the function f of x is equal to negative x squared plus 4, but the shaded region is now going to go, we're going to shade this part and this part, and we're going to go to where x is equal to 3. Okay. All right, this is a really important conceptual piece to this. The definite integral doesn't compute, so I sort of lied when I gave you that carpet analogy. I was sort of lying when I gave you that carpet analogy, because when we find the definite integral, we don't find the total area. What do we find? The net area. And how will the definite integral count each of these regions? It will count this region how?
Positive.
As positive, but it will count this region as negative. So how should my answer compare to my previous answer? It should be less. Does that make sense? That's an important conceptual thing to realize. That the way the definite integral works is that we'll count those as negative. For those of you that were comfortable with last night's video, you saw that, well, you didn't see this, but we could just extend. If I draw these rectangles below the curve, then when I take the height of the rectangle, which is negative, times the width, I get a negative number there. So that's why it outputs a negative, just by construction. Okay, so what am I asking you to find? I'm asking you to compute the definite integral. Fill out the rest of it. You fill out the rest. Check with your neighbor. So let's see here. We're computing the definite integral from what are my lim? Oh, that's what I was going to say. We call these the limits of integration. That's what I'd forgotten earlier. What do we call these? Or sorry, I just told you. What are the limits of integration here?
0 to 3.
Yeah, from x equals 0 to x equals 3. Okay, in this problem. Our function hasn't changed, so it's still going to be minus x squared plus 4, what? Do you need the dx?
Yes.
Oh boy, you betcha. You saw this last time. Remember when you looked at 5.1, you saw all those delta x's? Okay. In the limiting procedure, we replaced the delta x's, which was the width of the rectangle, with differential x, which is the which still stands for the width of those rectangles. So do you still need that? Yes. Okay. But it also sort of it gets wrapped up into the woodwork when you do the antiderivative. All right. So let's actually compute this by the fundamental theorem of calculus part 2. Rather than using Riemann sums to compute this area, okay, rather than using those Riemann sums that you saw in the video, we're going to go ahead and just give an antiderivative of this. What do I have to write? That evaluation bar from x equals 0 to x equals 3. Do you need that? Yeah. I emphasized that in my other class, and then I'd go around and half the people wouldn't put it. Yes?
Can I just put 0 and 3 for A and B?
Yes.
Okay, cool.
Okay. All right. So let's see here. This is going to be minus 1/3 times 3 cubed plus 4 times 3. And then I'm getting the hang of things. There's no constants here. This is a polynomial, so just to save myself some time, I know that's going to be 0. Okay, you're welcome to do that. Do look ahead on that. Okay, careful, will it always be 0 if the lower limit of integration is 0? No. If there's an e to the x or cosine of x, no. Okay? Or if there's a constant term, okay. So, let's see here. I think we get 3 cubed is 27 times minus 1/3. I think we get minus 9 plus 12. So I think we get 3 as the area of this shaded region. That's nice. Rarely do you get nice numbers in this procedure. How come? Because often you use the power rule, and the power rule often introduces fractions. So oftentimes these don't work out nicely. That's just life. What else do I want to say? How does this number compare to our 16/3 from before? Well, 16/3 is a number a little bit bigger than 5. This is the number 3. So what happened? The definite integral counted this region right here as negative. So it took our 16/3 and wrote it this way. It took our 16/3 and then subtracted this amount from it. By the way, that opens up a really interesting idea here that we can do with our definite integrals. So let me show you this, this property. I hope you have room for it. Okay. Let me show you this property. If I take the integral from a to b of f of x dx, I could break it up as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. In terms of what you saw in last night's video with the Riemann sums, one way you could imagine that is rather than adding up the area underneath the tire curve, you just go halfway or part way, you just go to c, and then you pick up where you left off, adding up the rest. And that's true. That's just a property of addition by its associativity. Okay. Where did I lose you on the property, or did I lose you on something before? Okay, on the property. So let's look at this problem here. How could we have done this problem? Okay. If I asked you for the definite integral from 0 to 3 of minus x squared plus 4 dx, what I'm saying is you could have gone from 0 to 2 of minus x squared plus 4 dx plus the integral from 2 to 3 of minus x squared plus 4 dx. Do you see what I did there? So I broke it up into 2 different pieces, adding up first from 0 to 2 and then continuing on from 2 to 3. Does that clarify?
So with the first not function.
Definite integral?
Yes.
Evaluate to same
of
6.
The property, would it be a to c instead of a to b?
Well, so this is what we started with. If it originally goes from a to b, you could stop off at c and then resume. Okay?
So we're saying c is between.
Great question. It actually does not have to be in between.
Okay.
It doesn't have to be in between, which is why we use c. Okay? So this was 16/3, and then in fact we could actually figure out what this would be. So what would that have to be? Help me out, folks. This would be negative 5/3, right? Because when you add them together, what do you get?
9/3.
You get the 9/3 or the 3 that you were supposed to. Okay? So what I'm saying is, rather than finding the total net area, we already found out that was 16/3. That's a 16. We already found out that was 16/3. We could then compute this, find out that it was a minus 5/3, minus 7/3, which would give us the 9/3 or the 3 that we were supposed to get. Okay? Questions on that?